Okay, so welcome back to particle physics and the standard model. This is lecture 42 and last class we inspected the PMNS matrix a bit. What is the PMNS matrix? It is the matrix that takes you from the mass basis to the flavor basis, okay, in neutrinos, right. And we parameterized it in the usual way as the the way that we used in the for the CKM matrix, and we found that the rotation angles in this case, unlike in the CKM matrix, were actually considerable. So that we understand that the neutrino flavors do mix a lot with each other, okay, unlike the quark flavors. And we also saw that the CP violation phase has large measurement uncertainties associated with it because it is indeed very hard to control neutrinos, that is what it comes down to. Okay. Now, all of this gave rise to the notion of unitarity triangles, where due to the orthonormality of the rows and columns we had this relation, right. And how do we interpret this relation? In the Argand plane, taking an example like this, we saw that you can write 6 of these relations as, you can rephrase them as 6 triangles basically on the Argand plane, right. And these triangles are very important notions for experimental physics, because as we saw here in this image by CKM Fitter, you could basically make independent measurements of the different CKM elements up to that angle over here, so that you really do not know what the relative phase is between the two sides of the triangle. So, that would mean you basically would draw circles with bands denoting uncertainties, and if those bands overlap at the right place, it tells you indeed that unitarity is true up to these measurement uncertainties. And this is an amazing plot because many independent measurements with many different uncertainty bands overlap at the right place, giving us more and more confidence that all this structure that we have been writing down is indeed true, because it picks out the unitarity in flavor space beautifully, correct. And from there we moved on to yet another use of the unitarity triangles, namely this allows us to write down a basis independent measure of CP violation. What is basis independent? Earlier we had seen you could write this as a CKM phase as a delta CP, or in terms of this epsilon in KK oscillations and other meson oscillations, but all of these depend on some sort of parameterization that you had to put in, right. So, it would be nice to have a measure of CP violation in the weak sector that is independent of all this, so that we really see what how much CP violation there actually is. That really is the CP violation, amount of CP violation in nature. Okay. Okay. So, we ended by writing down the Yarlskog invariant, which is indeed that basis independent measure, right, in terms of the combinations of these CK matrices. And in this lecture I promised to prove to you that this is indeed an invariant and there is a geometrical interpretation for it, right. But it was useful to write down the Yarlskog invariant in terms of the rotation matrix angles and the CKM phase, right, using the usual parameterization. That way we could see that if delta is 0, the Yarlskog invariant also goes to 0. Okay. All right. So, so that would just mean no CP violation, just to be complete. Okay. Let me begin this lecture by first pointing out who discovered this invariant. Okay. It is important to know physicist names. It was discovered by Cecilia Yarlskog, who I believe is a Swedish physicist, okay, and I think it is an amazing contribution that she made to particle physics. Okay. So, we will see in a second. You can actually go and read Cecilia Yarlskog's paper, it is very readable, It's one of the most beautiful papers I have read. Okay, so I highly recommend going and looking at the original source of this. Okay. So, I am going to claim that this Yarlskog invariant is nothing but 2 times the area, okay, of any of the unitarity triangles. Remember there are 6, right, any of the 6. Okay. How do I know that? Because let us go back to this unitarity triangle. Okay, let us go back to this one. What is the area of this triangle? Suppose I call this alpha, this is beta, and this is gamma, right? Can you tell me what the area of the triangle is now using your high school trigonometry, right? So, for that triangle, would you agree that the area is VUD, VUB star, VTD, VTB star, and then what? Sin beta, right? AB sin theta. Remember that formula? That is just what I have written here. Okay. What is this? This is nothing but the imaginary part of VUD, VUB star, VTD, VTB star, correct? See, that is exactly what this is, right, one of these basically. It is probably this one. Okay, I have probably not written it, but you can check it actually, it is one of these. So, this is basically one of these. I just switched notation a bit. Okay. So, this also tells you, right, that all 6 unitarity triangles have to have the same area. Why? Because this is invariant is what I am claiming, right. So, this is very easy to check whether these are all the same thing. You can check this in Cecilia Yarlskog's paper, you can check this yourself also, and I highly recommend doing this calculation yourself. Okay, but I am going to do it for you now, so that you can check against your own calculation. So, let me derive that for you. Okay. See, unitarity gives me conditions like these, right. I am going to write down 2 conditions so that it illustrates what we are showing here. We have VUB, VCB star equals 0, and I am going to call that equation 1. Okay. Then let me write down one more condition, one of those row column orthonormality conditions, VUS star plus VCB, VUB star equals 0. Okay. Now, what I am going to do is take equation 1, okay, multiply it with VUS star VCS, okay, multiplying that, okay. Not only that, I am going to take the imaginary part of that. What should this be? Obviously, it should be 0, right. If I take the left hand side of this equation, that is 0, right. Okay. So, that would imply, what would that give me? It gives me imaginary part of VUD, VCD star, VUS star, VCS plus imaginary part of VUS, VCS star, VUS star, VCS plus imaginary part of VUB, VCB star, VUS star VCS, right, equals 0. Okay. So, what is this now? That is absolutely 0, right. I just taken VUS star. So, that is a real number, VCS star VCS, that is another real number, right. So, I have sent that to 0 and that tells me that at least 2 of these up to a minus sign, right, are equal. See, just like that I got 2 unitarity triangles to have the same area, right. And then similarly, okay, suppose I take the second equation, okay, and then I hit it with the VCD star VUD, that is also 0, right. Now, go ahead and do this. Once again you will find that the VCD, see the VCD star hits the VCD, VUD star hits VUD, and the imaginary part of that combination of 4 elements is 0, right. So, now I will get equality between these two after I hit it with this combination, right. So, that should at the end of the day give me VUD, VCD star, VUS star VCS, imaginary part of that is minus of imaginary part of VUD VCD star VCB VUB star. This is yet another unitarity triangle, right. See, we have this which is the same as this and we have already equated it to 2 other combinations, right. So, I am not going to do all 6, you can go convince yourself that this is indeed true for all the 6 combinations that you can write down and hence all the 6 unitarity triangles. Okay. So, this shows that J is invariant. Or rather J is an invariant. Okay. Good. Okay. Are we happy now? Good. So, then we can move on after having settled CP violation, we can move on to another very important consequence of everything we have been doing so far. The very famous phenomenon called neutrino oscillations. Okay. Now, this name really confuses a lot of people, lot of physicists, especially students. So, I prefer another name that I have seen in the Tasi lectures of Andre de Gouvia, and that name is mass induced flavor change. Okay. So, every time you see neutrino oscillations, remember this might be a little more mouthful, but it gives the concept very clearly. It is mass induced flavor change. Okay. We will see exactly what we mean by this. Okay. So, let us start with a simple equation, okay, that captures how a neutrino state would evolve. Okay. And this, when I write ijk Roman numerals, sorry, Roman letters, it stands for the mass eigenstate. And when I say alpha, beta, gamma, that would stand for the flavor eigenstate. Okay, let me just write this down because it's important. So Latin or Roman index like I, J, K stands for the mass eigenstate of the neutrinos. Okay. And when I use Greek indices like alpha, beta, gamma, that stands for the flavor eigenstate. Okay. So, with that out of the way, what is the 0 and the 0? Those are space time indices. Okay. You will see in a moment what I mean by that. If I want to see how this evolves, okay, this state evolves over time and also in space. What is that? From the Schrodinger equation, that is just e power minus I p I x, right, where the p I squared is m I squared. So, here it is even more manifestly clear that I stands for the mass index, correct, the mass basis index. Okay. So, you agree with this much? Okay. And of course, it helps to write one more time I am going to write the PMNS matrix in this notation. So, instead of writing it as a column matrix I am just going to write it as a ket. Okay. The PMNS matrix, see explicitly I am now using alpha and I together here, so that it shows that there is rotation from the mass basis to the flavor basis, correct. So, if I write it this way, this relation should be obvious, right, using the unitarity again, correct. What is this? This is the sum of the mass basis masses, okay, summed over weighted by the PMNS matrix elements. So, this I just get from the inner product, okay, and then that is going to give me the squared mass of the electron neutrino in the Lagrangian. Okay, this is not some real mass. Okay, in the Lagrangian I am going to have some m e nu. I can always have other combinations also, m e nu, m e mu and so on. Off diagonal elements are always there. That is the whole point of this rotation from one basis to another. But if I just take the diagonal element squared, that is what this is. Okay. Okay. Now, here comes the notion of oscillations. Remember I said that it is much easier, it is not just much easier, it is exclusively only possible to make and detect neutrinos, okay, in flavor eigenstates. That is not mass eigenstates. Okay. So, that means, what does that mean? There is a mismatch of these flavor eigenstates. Okay. I am just going to write it this way now. With the mass eigenstates, I am going to write that like this. Okay. During propagation. Okay. So, what does this mean? suppose I make a neutrino here, okay, let's call it a nu e, okay, and then I let it go, right, during the propagation, right, there is no reason that at the time of propagation it is still a electron neutrino. Okay, there will be a mismatch. Why? During in the propagation is always in the the mass basis. So, we saw that here, right, literally when we wrote this down, right, this is what we mean by propagation. The evolution of the state during propagation, right, can only be written down for the mass basis, right, that is what Schrodinger equation tells us, correct. Okay, so that is what we are making use of here. Okay. If this is not clear, do not worry, we will add more flesh to this in a moment. So, I am going to illustrate this with a 2 flavor eigensystem, okay, or a 2 flavor system, let us just call it that. Okay. Imagine I do not have the tau neutrino, okay, that is what I am saying here. So, let us take the flavor, the electron flavor eigenstate to be composed of, I am just breaking down the PMNS matrix to a 2 cross 2 matrix, okay, that is what I have done here. Let us say it is an admixture parameterized by a theta, admixture of nu 1 and nu 2. Then what would be the mu 1? It is the orthogonal combination, right. Okay. And let us say this is true at t equal to 0. Okay. Now, how would this combination, so see nu 1 evolves according to e power minus I p 1 x times nu 1, right, and then nu 2 would evolve according to e power minus I p 2 x times nu 2, right. So, how would this entire combination evolve? So, I can then say that whatever that combination is, right, over time, I am going to put this under quotes, okay, because it is not really the nu e anymore, okay. It is just that combination would evolve as cos theta nu 1, oh I am sorry, I have to put in the evolution, which is e power minus I p 1 x nu 1 plus sin theta e power I p 2 x nu 2, right. That is what that combination evolves as over time. So, it is not clear what to call that combination. So, I am just calling it nu e of t within quotes. It is not really nu e now. You are not going to detect it, clearly you are not going to detect this thing as nu e, because you basically change the coefficients of nu 1 and nu 2, right, using this e power minus I factor, right. So, you can already see some notion of flavor change, right. I said mass induced flavor change, correct. Just like that, because you have a mass and because you have propagation, you change the flavor, right. So, where do the oscillations really come from? We will see, okay. To see that really, I have to do one more approximation to this, okay. I am gonna inspect these terms, the pix, right, in the evolution, it is EIT minus pi dot x, correct. I am using the 1 minus 1 minus 1 minus 1 metric, correct. And Since neutrinos, I know retrospectively that neutrinos are very light particles, and so in almost every situation I can think of, right, other than relic neutrinos actually, I have the speed of neutrinos just very close to the speed of light. So, I might as well call it the speed of light, which is 1 in natural units, right. If that is the case, then what do I have? I can write this as EI minus the momentum, which I am going to take to be in the z direction. Okay, I am going to take the propagation to be in the z direction. Okay, and I am going to pull out some L, which is the length, the distance travelled by the neutrino. Okay. All right. Now, what else can I do with this? So, this EI, right, because again the neutrino is so light, it is almost like a photon. So, EI is literally almost equal to Pi, correct, in this case Pzi, right. But I can do better actually. I am going to write this as an expansion. Okay. I am going to make use of the fact that the mass is in almost every situation one can think of always much smaller than the momentum. So that, okay, so what I am, so this is not an implied actually, just keep this as an aside so that you get it, you get some intuition for how close the energy is to the momentum, but we are going to actually do an expansion. The expansion is this, okay, the energy is what, it is this, and in the relativistic limit it is Pzi plus m nu I squared over 2 Pzi plus terms that are order m nu I to the 4th. Okay. So, doubly normalized, but basically these are very small. So, we are going to neglect that. Okay. So, I am going to wrap up this lecture by writing out this term using this approximation. Okay. So, what has happened now? So, EI is Pz plus this term, right. So, what is this term? Let me highlight with red. That term is nothing but this, correct, now, right. So, it is worth writing it down now. Pix is nothing but m nu I squared over 2 Pz I L. So, again to make life easier, I am just going to write it as EI L. Why? Because of this, right. You can once again do an expansion, you can put the Pzi inside and then you can neglect higher order terms, you are going to get just EI in the denominator. Okay. Might as well call it E, okay, in this case. So, I am going to now finally write the neutrino eigenstate having the flavor eigenstate, which is not really a one particular flavor eigenstate, after having traveled a distance L would now be e power, so there is an I here, so e power minus I m1 squared L over E nu 1 plus sin theta e power minus m2 squared L over E nu 2. So, I have dropped the nu when I am writing the masses. So, that should be obvious, right. M1 corresponds to m nu 1. Okay. So, okay, very good. So, that is what it is, and we will take up this expression in the next lecture and derive a probability of oscillation going from one flavor to another due to propagation. Okay, all right. I will stop here. Thank you. See you in the next class.